Okay, now you should be able to see my OneNote, right? Okay. All right. So basically, yeah, like I was saying, if you have a composite function, which is just f of g of x, and I need to take the derivative of this, then my derivative is just going to be the derivative of the outer function, which is f, so prime of x. Then you're going to take the derivative of the inside of the function, so g prime x. And we can do a few examples with this to see, make sure you guys have a hang of chain rule. So I'll do this one. F of x equals the square root of 5x minus 8. So f prime of x. I'm going to go ahead and work it out, and then you guys also work it out on the side, and then write whatever answer you get in the chat. So the first thing we're going to do is just rewrite this as 5x minus 8 to the power of 1/2. And then we're going to go ahead and bring down the 1/2. Have 5x minus 8 on the inside and subtract 1 from the power. And then we're going to multiply by the derivative of this inside function, which is just 5. And so after simplifying it a little bit, we'll get our final answer to be 5 over 2 times the square root of 5x minus 8. And that would be your final answer for that. And then one more example for chain rule is if I have f of x equals e to the power of secant of 2x. So the derivative is going to be, so the normal derivative of e to the x is just e to the x. In this case, since it's e to the secant of 2x, we keep the first portion the same, and then we have to take the derivative of this portion right here. And so the derivative of secant of 2x is secant 2x tan 2x multiplied by 2, because now we have to take the derivative of the 2x inside of the tan and secant to finish off the chain rule. So is there any questions on how I solved those last two problems before I move on? So I'm going to do one question also with horizontal tangents. So the question, it wants you to find the horizontal tangents if it gives you f of x equals cosine 2x minus sine squared of x. So if it asks you for the horizontal tangent, it just wants you to find where the derivative is equal to 0. So find horizontal tangent. And it'll give you a boundary from 0 to 2 pi most of the time for trigs, so that you don't have just repeats of values. So the first thing you're going to want to do in the case of something like this is rewrite your function. Rewrite your function in terms of one trig. So we could change cosine of 2x, for example, to 1 minus 2 sine squared of x, and that's just by using the identity for cosine of 2x. And then we have sine squared of x here. So now our angles are both just in terms of x. So that's the first step. And then we can simplify this to reading f(x) is 1 minus 3 sine squared of x. And then Now we take the derivative and we're going to set it equal to 0. So it'll be negative 6 sine of x times cosine of x. Again, by using chain rule. Um, and then from here, there's another identity you can apply to simplify it. And so you can make, so we know that 2 sine x cosine x is just sine of 2x. So we can, since there's a 6 out front, we can just know this would be negative 3 sine of 2x. And we can set that equal to 0. So then that's essentially us just saying sine of 2x is equal to 0. And sine is equal to 0 at k pi. So 2x equals k pi. And then x equals k pi halves. And then you plug in your various values for k starting from 0, just up until your x, just so that you get x values below 2 pi. So in this case, it would be x equals pi halves and 3 pi halves. Okay, any questions on that one? Now let's go over implicit differentiation. There were some students who came into peer tutoring who were having trouble with this, so I'll go over a couple of good problems for this. Okay, so the first one, it's just going to be find basically what is dy over dx equal to. And the function will be y tangent of 2x equals x sine of 2y. And remember, when you're taking the derivative of all this, it's in terms of x. So if we apply product rule to this first portion over here, we get that dy over dx, so the derivative of y, times tangent of 2x, plus, now we keep y the same, and then we take the derivative of tangent of 2x, which is just 2 secant squared 2x, and the 2 comes down because of chain rule again. So then we go to the right side. We can take the derivative of this portion. So the derivative of x is just 1, so I'll keep it as sine of 2y. And then keep x the same and then take the derivative of sine of 2y, so that'll just be 2 cosine of 2y. And then you also have to remember that you're taking the derivative of this y function now, so you have to include your dy over dx at the very end. Now from here, your next step is going to want to be to isolate any terms with dy over dx onto one side. So that would be these two terms. So what you could do is keep this dy over dx tangent of 2x on the left side, and subtract over the 2x cosine of 2y dy over dx on the left side as well. So now I have x2 cosine 2y dy over dx on the left side as well, and then move everything else to the right side. So sine of 2y stays there, and subtract over this y2 secant squared of 2x. So minus 2y secant squared of 2x. Now you're going to go ahead and factor out your dy over dx. They're common in both terms. So tangent of 2x minus 2x cosine of 2y. And then that's equal to sine of 2y minus 2y secant squared 2x. And then you can just go ahead and divide over this term onto the right side so that you have dy over dx isolated. So dy over dx is equal to sine of 2y minus 2y secant squared 2x divided by tangent of 2x minus 2x cosine of 2y. And so this would be what your final answer for dy over dx is. Yeah, so you're going to need to know all the trig derivatives and arc trig derivatives also. It won't be given on your exam. And then another example for implicit differentiation is if they ask you to find the second derivative. A lot of students are having trouble with this as well. So if I have something that's like e to the y minus y equals x. Okay, so first we're going to take the derivative with everything with respect to x. So we'll have e to the y times dy over dx minus dy over dx equals 1. Again, factor out your dy over dx. In my parentheses, I'll have e to the y minus 1 equal to 1. And then I'll just have dy over dx is equal to 1 over e to the y minus 1. So that's my first derivative. And then we're going to have to take the second derivative of this. So we have dy over dx already on one side. So now this will just become my second derivative. And so from here, we can just take the derivative of the right side, which is basically just e to the y minus 1 to the negative 1. And so the derivative of that would be negative e to the y minus 1 to the negative 2 times, and then you remember with chain rule you have to take the derivative of this inner portion, which is e to the y. But since everything's in terms of x, you also have to include the dy over dx. And we know what each of these variables is, so we can keep, we know what dy over dx is rather, so we can just plug in 1 over e to the y minus 1 or dy over dx, and basically if we go ahead and plug everything back in, our final answer will be negative e to the y over e to the y minus 1 cubed. So the only extra step for finding the second derivative is you're going to have to plug back in dy over dx, which you solve for in the first portion of the question over here. So are there any questions on how I did this one, or implicit differentiation? Okay, sounds good. So now I can move on to derivatives of inverse trig. Okay, so first I'm just going to list out all the different, what all the different derivatives are so that you have an idea. So the derivative of arc sine of x. Well, actually, I'm going to do it in terms of u because it's rare that they'll just give you arc sine of x. So u could be anything, like it could be x squared, x cubed plus 1, anything. So derivative of this is going to be the derivative of u over square root of 1 minus u squared. It was just arc sine of x though, and it would just be 1 over square root of 1 minus x squared. But it'll hardly just be arc sine of x. So then I'll do the same thing with cosine or cosine, except, and this is the same as sine, except you have a negative in the front. And again, if it was just arc cosine of x, it's negative 1 over 1 minus x squared. And so that's the sine and cosine. And then if I have arc secant of u, so if I have arc secant of u, this one is going to be du over the absolute value of u times the square root of u squared minus 1, and then just arc secant of x is 1 absolute value of x, and then x squared minus 1. And then it's basically the same thing for arc cosecant, except you have a negative out front. So it's the same thing. Negative 1 over absolute value of x, and then x squared minus 1. Okay, and then the tangent cotangent. So arctan of u is du over 1 plus u squared, and then normal arctangent x is 1 over 1 plus u squared. And then same thing again for arc cotangent, except we have a negative in the front. Okay, so that's all of them. And now we can do an example problem with these. So let's do f of x is 4x squared arctangent of x plus 1 minus sine of x, the square root. Okay, so you guys work this out on the side, and I'll just do it and explain my way on how to solve it. So the first portion, I'm going to go ahead and apply a product rule. So I'm going to take the derivative of this part first. So I'll have 8x, then I'll keep my arctan x constant. And I'm going to go ahead and take the derivative of the arctan of x and keep the 4x squared constant, so it's 4x squared. And arctan of x, like we already went over, is 1 over 1 plus x squared. And then I'm going to take the derivative of this 1 minus sine of x, which is really just 1 minus sine of x to the power of 1/2. So I'm going to apply chain rule, 1/2, 1 minus sine of x to the negative 1/2. And I'll take the derivative of the inner portion, and the derivative of negative sine of x is just negative cosine of x. And you can simplify this however you want, but that would be your final answer. Okay. And I think I'm only going to go over one example for derivatives of inverse trig because it's relatively straightforward. You just have to kind of use the formulas that we went over before. So now I'm going to go over the derivatives of natural log and log sub a b. So this And so the formula you're going to want to use is the derivative of log a x is equal to 1 over x. So it's basically the same as ln, except now we have the ln of a. And the derivative of ln of x is 1 over x. And the reason it's just 1 over x is because if I have ln of e, it's just equal to 1. Okay. So I'll go over some examples with this. So this is a good example. F of x is equal to ln of tangent of ln of x. So the first thing we're going to do is we know now that I'll write a main formula for ln, and it applies to log as well, but d over dx ln of u is du over u. If you write everything in terms of u, it makes all these equations a lot simpler. So now if I have ln, which is my outer function, and this is u, tan of ln of x, so I know that I have to first take the derivative of u, which is this. So I'm basically taking the derivative of tangent of ln of x. So we know that derivative of tangent is secant squared ln of x. And then we have to take the derivative of the inner portion, which is 1 over x. And the formula for taking the derivative of ln is du over u. And so my original u is just tangent ln of x. So then I can rewrite this as secant squared ln of x over x tangent ln of x. That's my answer. Okay, does that make sense to everybody? Or was that kind of confusing? I'll go over one more example with a yeah, it was over u. So okay, so the absolute value is just written as like a notation thing. So like it's so that you don't have to write ln parentheses and ln in parentheses again. And also like, you can write ln of x with absolute values or parentheses. It doesn't really matter. It just depends on the notation your teacher wants. Okay, so I'll go over this one with the log example. So log base 4 x to the 4 e to the x. And so I forgot to add this, but basically you could also write this as du over u times ln of a. So again, we're going to take the derivative of u first. So the derivative of x to the 4th and e to the x, we're by product rule. So 4x cubed e to the x plus x to the 4th derivative of e to the x is e to the x. So that's du. And then our u is x to the 4th e to the x. So this is du. This is u. And then ln of a is 4. So ln of 4. And then again, you can simplify this however you want, but this is a way to apply the formula. So if there's no questions on that, I'm going to go ahead and move on to logarithmic differentiation. And all of these topics are related to each other, but they ask you different types of problems for these things. So, okay, this one's kind of long, but you'll most likely see something like this on your exam. So it's y equals x to the fifth, and then 1 minus 10x, and then x squared plus 2. And you could do the derivative of this by just doing quotient rule, but the quick way to do it by using logarithmic differentiation is to first ln both sides. So ln of y equals ln of this entire thing. So that's the first step. And then by using log properties, we know that we could rewrite this as ln x to the fifth minus ln of 1 minus 10x minus ln of x squared plus 2 to the power of 1/2. And I'm just rewriting that because we can go ahead and move that power in the next step to the front of the ln. So now I'm going to make the derivative of everything left and right side. So the derivative of ln of y is it's 1 over y, but it's multiplied by dy over dx because we're taking everything with respect to x. So basically it's dy over dx over y. And I'm going to take the derivative of ln of x to the fifth. So du over u, so 5x to the fourth over x to the fifth. Now I'll take the derivative of ln minus 10x. So the derivative of u is negative 10 over 1 minus 10x. And then for this one, I'm going to go ahead and just move this 1/2 right here in front of the ln and take the derivative of ln of x squared plus 2. So that's going to be 2x over x squared plus 2. So is there a question? Going to be minus and then plus since the denominator is being multiplied? Oh, no. If whatever's in the denominator gets subtracted. So like, even though I think you're saying these two are multiplied, you still subtract both of them as individual terms. Yeah, and with this, if you're talking about this negative, I'm about to change that in the next step. So I can go ahead and simplify this to 5 over x plus 10 over 1 minus 10x. And then minus, cancel these twos out, so x over x squared plus 2. And then from this step, you just need dy over dx. So we can go ahead and multiply this y over. So dy over dx is equal to 5 over x plus 10 minus 10x minus x over x squared plus 2. All of this multiplied by y. And we know what y is from the beginning of the problem. So then we plug that thing into my final answer. So it's just going to be and y is just that super long function, which is x to the fifth over 1 minus 10x x squared plus 2. And so that would be the final answer using a logarithmic differentiation. So done with that. And then there's one more example I go over with logarithmic differentiation. So if I have y equals 1 minus 3x square root in the bottom. Are you talking about this step right here that I did when I set it up as ln of x squared plus 2 to the power of 1/2? Yeah, so I just moved the 1/2 to the front of the ln by using the log property so that I don't have to deal with the square root in the problem. Okay, so moving on to this problem, I'm going to do the same thing. I'll ln both sides. So and then I'm going to do the same thing and apply that log property to move the cosine x to the front. So I have this right now, and then I'm going to have the same thing when I take the derivative of the entire left and right side. I'll have dy over dx divided by y, and then I can apply product rule. So I'll keep cosine x the same. I'll have -3 over 1 minus 3x by taking the derivative of the ln function. And then I'll have the derivative of cosine x, which is negative sine of x. And then I'll keep ln of 1 minus 3x constant. Then we can simplify this down after we move the y over. So dy over dx equals -3 cosine of x minus 3 of x minus sine x ln of 1 minus 3 of x. All of this multiplied by y. And then our final answer will just be dy over dx is equal to -3 cosine of x over 1 minus 3 of x, or 3x, and then minus sine x ln of 1 minus 3x. And then y was just 1 minus 3x to the power of cosine x. Okay, so that's basically logarithmic differentiation. Are there any questions on that? So I'll move on to related rates now, which I'm pretty confident nobody likes. So I'll show you this one or two related rates example problems. I got these from your homework. So we can go ahead and work these out. So the first one is particles moving along a hyperbola. It gives you the function xy is equal to 8. Yeah, so the examples on your graded homework are pretty much the level of difficulty you can expect on your actual exam. In fact, they're probably harder examples than you'll see on your test, so they're good ones to work out. So for this one, it's asking you how fast the x-coordinate of the point changed at that instant. So basically, it's asking you what is dx over dt equal to. So you want to first find out what the question's asking you to solve for, and then you need to set up an equation involving that variable and the function they give you. So they give you xy is equal to 8, and they give you the point 4 comma 2, and they give you dy over dt also. So they say dy over dt is equal to -3 centimeters per second. Okay, so basically the function it gives you is xy. So you're first going to have to take the derivative of xy with respect to dt. So we'll get, by doing a product rule, we'll just get dx over dt times y plus x times dy over dt. So in this case, it's kind of like implicit differentiation, except you're taking everything with respect to x and y, or with respect to t, sorry. So that's equal to 0. And then we're going to try to isolate for dx over dt, because that's what you're trying to solve for. So we'll keep dx over dt times y on the left side, and on the right side we'll move over negative x times dy over dt. And then we can just plug in the variables that they gave us at the beginning. So we know that our points are 4, 2, so x is equal to 4, y is equal to 2. So we know it's dx over dt is equal to 2, times 2. And then x is negative 4. And you know that dy over dt is equal to negative 3. Now you have everything you need to solve for dx over dt. So now we know that dx over dt is equal to 12 over 2, which is equal to 6 centimeters per second. So does that example make sense to everybody? Okay. So now we can go over this example with the triangle. So let me see this one. So I mean, you can make a diagram if you want. You don't have to. I never used to make diagrams because I just didn't want to, but if it helps you, then you can. So you could just draw out a triangle and then the altitude and the base, whatever. So I know that in this case, it's saying altitude is increasing and the area is increasing, and then it's asking you what rate is the base changing, and then it gives you specific conditions. So I know that I'll call altitude like little a. So dA over dt is equal to 1 centimeter per minute. And I know that I'll call area big A. So I know that dA over dt is equal to 2 centimeters squared per minute. Then I need the equation involving altitude and area. So we all know that area is equal to 1/2 base times height, or in this case, they just call it altitude, so little a. And then I'll take the derivative of both sides with respect to t. So dA over dt equals 1/2, and then I'm going to apply chain rule with b and a. So I'll have dB, which is the base, over dt times a plus b times dA over dt. Okay, and then it gave you specific conditions. So it said, okay, so we know that d over dt is 2, so we can plug in 2, 1/2, and then we're solving for dB over dt. It gave you a specific altitude of 10 from here. And then, oh yeah, and then the base is 20, but the way you get the base is, they said that the area is 100 centimeters when the altitude's 10. So quickly on the side, you can just do, okay, 100 equals 1/2 times base times 10. And so if you solve for b, you'll just get 20. So that's how you get 20 over here. And then you know dA over dt is equal to 1. Okay, so then multiply the 1/2 over, so 4 equals 10 times dB over dt plus 20. Subtract over the 20. So negative 16 equals 10 times dB over dt. And then dB over dt equals negative 1.6 centimeters per minute. And that's your final answer. So does that make sense to everyone also? So that's related rates. That's done. Yeah, these are basically the types of problems you'll probably see on your test. You might see something with like asking you for the rate of change of the angle, which everyone finds confusing. But really for that, you just have to set up a trig relationship between whatever you want. It could be sine, cosine, tangent. The angle one might be difficult for some of you, but it's really just the same as the rest of the problems. You just write your givens and then set up a relationship involving both of them. Okay, so I'll go over linearization now. Okay, so if it already said in the question that it's a decreasing base, then you just write the absolute value. So you just write the positive answer of that, because it's implied in the question that it's already decreasing. Okay. Okay, so the formula for linearization is L of x is equal to f of a plus the derivative at a times x minus a. And the purpose of this is for us to approximate values that we don't know. So like we know that the square root of 4 is 2, but we don't know what like the square root of 4.1 is. So this helps us do that. So one example is square root of 4.6. So the first thing you're going to need to do is figure out, okay, what equation are they referencing? So obviously they're talking about just the square root of x. And then you need to find a set of a point A that you know, and that's close to this. So we all know that 4 comma 2 is defined on y equals the square root of x. And then you're going to have to find the derivative of this function. So it's 1/2 x to the negative 1/2. So that's what you have to do. First find the equation it's referencing, find a point that's close to it on this function, then take the derivative of that function, and then you can go ahead and set up your linearization equation. So f of a, so we know that this is a, f of a is 2, and then f prime of a, so if I plug in 4 for x over here, I get 1/2 4 to the negative 1/2, which is just 1 over 2 times 1 over 2, so it's 1/4. And then x minus a, and again, a is 4. That's my equation. And now if you want to evaluate specifically at 4.6, we can just say L of 4.6 equals 2 plus 1/4, 4.6 minus 4. And then if you go ahead and simplify and solve everything, you should get 2.15. And if you plug it in a calculator, you'll probably get some like 2.149, something close to 2.15. Okay, so that's linearization. It's a pretty simple topic, so I don't want to spend too much time on it. Does anybody have any questions on this? Okay, so it's with differentials and error, it's nothing you haven't seen before. It's just kind of going one extra step. what you have been doing. So if I have an example that's y equals 3 plus x squared, the square root of 3 plus x squared, and I say x is equal to 1 and dx equals 0.1. Okay, so the first thing I'm going to do is solve for dy over dx. So that's 1/2 3 plus x squared to the negative 1/2 times 2x. And then I'm going to simplify this a little bit. So cancel out the 2's. So I'll just get x divided by the square root of 3 plus x squared. And then the last thing you're going to have to do for these types of problems is just isolate dy. So x over the square root of 3 plus x squared, and then go ahead and move over your dx to the right side. And we know that x is 1 and dx is 0.1. So if I plug in everything and I solve for dy, I get 1 over 3 plus 1 times, oh, the differential is negative 0.1, sorry. So negative 0.1, I get dy is equal to 1 over, basically negative 1 over 2 times 10. So I get negative 1 divided by 20. So that's something with differentials. And then something with air that's probably more relevant to your exam would be a question like this. So it says the radius of a circular disc is given 24 centimeters, maximum air 0.2 centimeters, and then it wants us to find the maximum air and calculating the area and the relative air. And percentage air is the same thing as relative air, just multiplied by 100. So I'm not going to do part C. But so okay, part A. So the first thing we're going to have to do is set up an equation for area, because that's what it's asking us for. So pi r squared. Then we're going to take the derivative with respect to the radius, because the radius is the one that's going to have the air associated with it. So we get 2 pi r, and that's it. Yeah, GA over dr is 2 pi r. Memorize area and volume equations. So you have to memorize, I mean, for some things, like the area of like a circle, you probably shouldn't know. Volume equations, like it might give you like if it's a sphere or something, you won't have that. If you have something like a cylinder, just try to know the volume equations it gives you. Like unless it's some weird shape, you should know the volume equations for it, the area equations associated with them. But they may or may not give it to you. I'm just not sure. Okay, so same thing. Then we're going to isolate dA. So 2 pi r times dr. And now we have everything we need. So dA is 2 pi. The radius is 24, as it's given in the question. And then our max air is 0.2. So then if you go ahead and calculate this, you'll get 50.15 centimeters square, and that's the maximum air that you would calculate. And then for part B, it's asking us for the relative air, and the equation for that is basically just dA over A. So dA is, remember, 2 pi r dr here. A is pi r squared. So basically it's r is 2 pi r dr is just going to be 9.6 pi and then divided by pi times 24 squared. And then you'll calculate out 0.017, and that's your relative error. So it's basically comparing your error from it's basically compared your max error to what the ideal area should be. That's your relative error. Okay. So does that make sense to everybody? Okay, so now I can go over time. Okay, so a bit on time right now. So max and min and critical points. Okay, so I'll start off with a really easy example, and you guys should be able to solve this one on the side pretty fast. It's a pretty easy one. So f of x equals x plus 4 squared, and we need to find whatever max or min there is. So we're going to take the derivative. We'll get 2 times x plus 4. Then, in order to find your critical points, you're going to set your derivative equal to 0. If I set this equal to 0, I'll just get x is equal to negative 4. Then you're going to go ahead and create your number line. Put your critical x value on it, so negative 4. And then you're going to plug in points after and before negative 4 to see what their sign would be based off of your derivative equation. So if I plug in, for example, 0, I'll get a 2 times 0 plus 4, which is 8, so that's a positive value. If I plug in something before negative 4, I'll get like 2 times negative 5 plus 4, which is negative 2, so that's a negative value. And then this basically tells you the direction of your slope. So if this is a negative sign, that's telling me that my slope is downwards. This is a positive sign. My slope is upwards. And if you imagine it like this, we would consider this a minimum. So at this point, at x equals negative 4, yeah, you could take the second derivative test to see if it's positive or negative. And then, as long as you know your rules of concavity, then you could determine if it's a min or a max. So if it was concave up, it would be positive and you would have a minimum. So yeah, you could use that as well. Yeah, based off of the first derivative test, we get that x equals negative 4 is a min. And then if you wanted to find the values, you could just plug in negative 4 back into your original function to get a y value for that. So that's pretty straightforward. And then I'll go over an example where you can find you need to find the values of a and b in order to get the critical, and it gives you the critical points. So kind of test whether or not you know how critical points work. So the question asks to find a and b. It says f of x is equal to 2x cubed plus ax squared plus bx. And it tells you have a critical point at x equals negative 1. And it tells you f of negative 1 is equal to negative 2. So that's what you're given. So the first thing you're going to want to do is take the derivative again. So 6x squared plus 2ax plus b. And we know that this is going to be equal to 0. And we're given an x value as well. So we know that so it's 6 times -1 squared plus, we don't know what A is, we don't know what B is. Okay. Oh yeah, so we don't know what A is or B, but we have this set up. And so we can simplify this to say 6 minus 2A plus B is equal to 0. And then this will be enough for us to figure out both variables. So then we also know that f of -1 is equal to -2. So we can set up something with this equation. So we know -2 is equal to 2 times -1 cubed plus A times -1 squared plus B times -1. And if we simplify this, it's -2 equals -2 plus A minus B. So we could simplify this a little, and so you would just get A minus B is equal to 0. And then you guys go ahead and solve for A and B and tell me what you get in the chat. I think this is just a good problem to work out. A equals B, so let's see if that works. I haven't actually solved this one out. So based off of this one, you would just get we said A is equal to B, so then 6 minus 2A plus A equals 0, so negative A equals -6, so A equals 6 equals 6. Yeah, I'm getting A and B both equal 6. I haven't worked this one out, so if anybody gets something different, just let me know. But I think that's what it is. Okay. And then I'll go ahead and start on mean value theorem. Okay, so there's 3 conditions for this one. F of x is continuous on the closed interval a comma b. F of x is differentiable on the open interval a comma b. And then okay, well, if we're going to include this third condition is only if you're applying Rolle's theorem, but f of a equals f of b, but I'll put in Rolle's, which is just a specific application of MVT. That's just for Rolle's theorem, and it would tell you that if f of a equals f of b, then f prime of c equals 0 somewhere on that interval. But with MVT, then if these 2 conditions check off, then there is a number c such that a is less than c is less than b, and f prime of c is just equal to f of b minus f of a over b minus a. So this is just saying basically there's a point where the average slope is equal to the instantaneous slope on the interval. Okay, so an example, it's going to ask you to find the values of c, and only if MVT applies. So it's going to give you x cubed plus 2x squared minus x on the interval -1, 2, and it'll say find c if MVT apply. So you guys go ahead and work this off on the side and let me know what you get for c. Yeah, so the f prime of c equals f of b minus f of a over b minus a is the third condition. It's not a condition, it's like the conclusion. So you only need f of x to be continuous and differentiable. And if those two things are true, then f prime of c is equal to f of b minus f of a over b minus a. It's not really a condition. It's more of a conclusion. Okay, so I'll go ahead and work this out too. First thing I'll do is take the derivative. So 3x squared plus 4x minus 1. And then I'm going to find f of b minus f of a over b minus a. So basically f of 2 minus f of -1 over 2 minus -1. F of 2 is equal to 14. F of -1 is equal to 2. 2 minus -1, which is just going to be 3. So is this going to be equal to 12 over 3? So this is equal to 4. So that's the right side, and then my left side is this portion right here. But instead of x, you're going to want c because it's asking you to find that specific c value. So now it's going to be basically 3c squared plus 4c minus 1 is equal to 4. And move everything to one side. So 3c squared plus 4c minus 5 equals 0. And then for this one, I chose a problem you can't factor on accident. So if you use like a calculator or something and solve for c, or use quadratic equation or formula, whatever, you get c is 0.78, and you get c is equal to -2.11. Now, I want you guys to tell me if I would use both of these values as my answer or just one of them, and which one would I use? Okay, yeah, perfect. Just because I need it to fit in my interval -1, 2. So yeah, good job. It would just be this one. And make sure to keep that in mind when you're going to have a question you can factor, but discount the value that doesn't fit in your interval. Okay. Okay, then I'm kind of going to go back to critical points and min-max, except I'm going to be specifically talking about increasing, decreasing intervals, and then concave up and concave down. Okay, so I'll write out the conditions for everything first so that makes sense to everybody. So if the derivative is positive, increasing. If the derivative is negative, decreasing. Then we look at the second derivative to determine concavity. So if the second derivative is positive, concave up. And if the second derivative is negative, concave down. Okay. And what does concave up and concave down tell us? Well, if it's concave up, it's going to look like this. Means you have a minimum. And that's when you can, I think one of you mentioned you could use the second derivative test to determine if you have a min or max. So concave up tells us we have a minimum. Concave down looks like this. Means we have a max. Okay, so that's basically all the rules, I guess. So then I'll go over a few examples where you're going to need to find the interval of increasing and decreasing and the intervals of concave up and concave down. So I have f of x equals x cubed minus 12x plus 2. Okay, so again, you guys solve this on the side and let me know what intervals you get, or just do it so that you could get some extra practice. So the derivative of this is 3x squared minus 12. We're going to need to find our critical points. So we're going to set our derivative equal to 0. And then I'm going to factor out a 3. So I get x squared minus 4 is equal to 0. And I'll get x equals plus or minus 2. From here, I'll make my number line again. So positive 2 and negative 2. And my signs, so if I use, this is my derivative. Anything past 2 is positive. Anything in between negative 2 and 2, so for example 0, would be negative. Anything below negative 2 would give me a positive value again because this x is squared. So that's how my signs are. So it's increasing here, it's decreasing here, it's increasing again there. So the intervals of increasing are negative infinity to negative 2, and keep in mind that it's non-inclusive to the negative 2 value, because at that point we have it switch from increasing to decreasing. So at that point it's a horizontal tangent basically. And then we're going to union this with 2 comma infinity, and then it's going to be decreasing from negative 2 to 2. And then we could say I have a min at right here at x equals 2. I have a max at x equals negative 2. And then we're going to go look at the concavity for this. So if f prime of x equals 3x squared minus 12, and I want to know where it's concave up and concave down, I'm going to need to take the second derivative. I'll get 6x. And you're going to have to set this equal to 0 also to find possible inflection points. So this is not, these aren't critical points, but these are inflection points. So 6x equals 0, x is just equal to 0. I make another number line. Anything past 0 is positive, anything below 0 is negative based off of this function. That means over here I have concave down, over here I have concave up. If you have a point and the concavity switches from down to up or up to down at that point, then you have an inflection point. So I have an inflection point x equals 0, and I'm only writing the x values, but remember you're going to have to find the y values for min max inflection point by plugging those x values back into your original f of x. So that's my inflection point, and then the intervals of concave up are 0 to infinity, concave down, negative infinity to 0, and yeah, that's about it. So that's really just an example where I ask you min, max, inflection point, concave up, concave down, increasing, decreasing. That has all of it in the question. So, okay, and are there any questions on that? So mean value theorem is done. Increasing, decreasing, concavity. Oh yeah, also move to L'Hopital. So that's topic 12. And how's time? Oh, time's pretty good. Okay, so you need to apply L'Hopital when you have an indeterminate form in your limit, and you're evaluating the limit. So I'll go over all the indeterminate forms first. So 0 over 0, infinity over infinity, infinity minus infinity, 0 to the power of 0, 1 to the power of infinity, infinity to the power of 0, and 0 times infinity. Yeah, you can go ahead and ask something about linearization. Yeah, I think you should be, well, if your professor didn't go over it, then probably not. I remember when I took the course, though, we did get questions about relative error and max error. But it's essentially the same thing as just using normal differentials. You just need to apply it to a word problem. But it's the same exact concept. Those are the indeterminate forms. And then, basically, you guys should all be familiar with L'Hopital. You take the derivative of the top and then the bottom until you get something that's not indeterminate. So, for example, and you don't always need to use L'Hopital either. So keep in mind that sometimes they'll give you limit question can solve normal that look hard, but you can solve them normally. Okay. Okay, so this is one example. So right off the bat, if I plug in 0, I'll get 0 over, what's that? Yeah, I'll get 0 over 0, which is indeterminate. So then I'm going to apply the L'Hopital rule. I'll get limit as x approaches 0. I'll take the derivative of the top. I get 2. If I take derivative of tangent inverse of 8x, I get 8 over 1 plus 64x squared. And then I can rewrite this as limit as x approaches 0 of 2 times 1 plus 64x squared over 8. And now if I plug in 0, I'll get 2 times 1 plus 0, which is 1 over 8. So 2 over 8, or just 1/4. So that one's kind of simple example. And then I'll go over a little more complicated example. So if I have limit as x approaches negative infinity, and my question is x ln 1 plus 4 over x. If I plug in negative infinity, I'll get 0 times negative infinity, because this x portion will be negative infinity. 1 plus 4 over infinity is 0. And ln of 1 is 0. So I'll get 0 times infinity, which is indeterminate. So I'm going to go ahead and use L'Hopital's rule again. And for this, it looks like they're being multiplied, so you have to somehow make it a fraction. So you never want to make the ln in the denominator. Keep that in the numerator, move the x. And that can be an x, x squared, x cubed, whatever it is. Move it to the bottom. So this becomes x to the negative 1. It's the same thing, but now I put in the denominator. And now I'll get, yeah, so did you just join the exam review by chance? Okay, yeah. So at the end of, after I go over all the topics, I'll go back to show you the question I did on here. Okay, so staying with this question, now I'll take the derivative of the top and bottom. Oh, why is this question indeterminate? So if I'll try to evaluate from the beginning, I have negative infinity, right, for x. If I plug in negative infinity for x here, I get 4 over negative infinity, which is 0. I get 1 plus 0, which is just 1, and then ln of 1, which is 0. So if we go back here, infinity times 0 is indeterminate. Oh yeah, so you're going to have to take the derivative of the top and bottom. So on the side, let's take the derivative of ln of 1 plus 4 over x. So the derivative of this would be 4x. So negative 4x to the negative 2 is du, and then u is 1 plus 4 over x. And then if I take the derivative of this portion right here, I get negative x to the negative 2. And then from here, I can immediately cancel terms out. I can cancel this thing out with this, and the negatives out too. So then I have limit as x approaches negative infinity of positive 4 over 1 plus 4 over x. I plug in negative infinity now, I'll get 4. This will go towards 0 over 1 plus 0. So I'll just get positive 4 as my answer. Does that one make sense to everybody? Oh man, they gave you guys a lot of topics for this test. Okay, so I'll go over, oh yeah, this one's also good. So I'll go over an example. Uh, okay. One over x. Okay, so the first, you're gonna have to kind of combine logarithmic differentiation. No, sorry, not logarithmic differentiation. You're gonna have to apply that same concept. So we're gonna have to first make this into y equals limit as x approaches 0 from the right. Okay, so this is the first thing you have to do. And then we have to ln both sides. So ln y is x approaches 0 from the right. And actually the ln starts from the, technically the ln starts before the limit, but there's a rule where you can change the place of the limit and the ln. So I just put it immediately in front of where I need it to be. So from here, I can do ln of y equals limit x approaches 0 from the right. And I'm going to drag this 1 over x to the front. Ln of 1 plus sine 3x. Okay. Okay. And then I'm going to apply the L'Hopital rule again, because you would get an indeterminate if you did the limit from here immediately. So we'll get ln of y equals limit x approaches 0 from the right, basically ln 1 plus sine 3x over x. We go from here now, take the derivative of the top and bottom. We'll get so du over u, which is a 3 cosine 3x. over 1 plus sine 3x, and then the derivative of x is just 1. So now, if I plug in, so I'll simplify this. So ln y is equal to limit x approaches 0 from the right of 3 cosine of 3x over 1 plus sine of 3x. If I plug in 0 now, I'll get cosine of 0, which is 1, times 3, which is 3. And then I'll get that over 1 plus 0 because sine of 0 is 0. So now I'll have ln of y equals basically 3. But I need y, not ln of y. So I'm going to exponentiate each side. And I'll get rid of this ln. And I'll have y is equal to e cubed. Does anybody have any questions on how I solved that problem? Okay, so I think that's all for L'Hopital. See what's left. I have just optimization and then antiderivatives left to go over. All right, and we're good on time. Okay, so topic 13. Optimization. So, I have the problem over here. I'm pretty sure this was y'all's homework problem for optimization. Even this might be something more complicated than you'll see on your test, but this is definitely something you'll see on your, probably see something similar like this to your final exam, some sort of like multi-step optimization problem, or it's not completely straightforward. So somebody tell me what's the first equation I should set up with this problem. Unit next to the 10. Oh, that's supposed to read, I think centimeters cubed, but it cut off when I tried to transfer it over. Volume of rectangular prism. Yeah. Perfect. So you're going to need to write your volume equation first, which is just V equals length times width times height. And then since you have 3 variables, you need everything in terms of 1 variable. So what we're going to do is, it tells you in the question, the length of its base is twice the width. So we know that L is equal to 2 times W. So let's go ahead and fix that. So 2W times W times H. And then this goes to V is 2W squared times H. And then we need to solve for H. And so somebody tell me how I'm going to be able to solve for H. The final exam's not, it's similar to the first 2 exams. It just has a few more problems that you have to, it's basically like the hard problems that they go over in the lectures, they put on the final exam. Like anything kind of confusing that they didn't include on the first 2 exams, they'll probably include that on the final. But I can't say for sure, because I'm not sure how the finals have been the last couple of semesters. Plug in volume and I'll, yeah, rearrange for H. That's how you solve for H. So it gives you that the volume is 10. So we know 10 equals 2W squared times H. If we rearrange it for H, we get 10 over 2W squared. Okay. Now we have an equation for everything, basically. Now we're going to have to work with the cost. That's what it's asking us for, to find the cheapest possible cost. Okay, so what do we know? We know cost is equal to $10 per square meter for the base. And so that would just be 10. And then, okay, so it's $10 per square meter for the base. And so what would I write in this parentheses then? It's just asking for the base. So it's basically just asking for this portion right here. Okay, and then also for our cost is going to be $6 for the sides. So everything that's not the base. So what would I include here? 6 times 2 WH times 2, yeah, plus 2 LH, yeah. Because it's a container, you're going to have, well, and it's an open container, so you have 5 total sides. We already accounted for the base. So it's going to be 6 times 2 WH plus 2 LH. And so that should account for everything in the cost. Yeah, because it's asking about the sides. Yep. Okay, so then from here, everything's in term. Oh, now we need to substitute back in H for when we rearranged it in terms of W. So everything's in terms of W. I'll just call cost C. 10 times 2W squared plus 6 2 times W times 10 over 2W squared plus 2 times 2W, which is L, times 10 over 2W squared. Okay, so then we'll get 20W squared. We go ahead and work this out. So what is that? That's 6. That's, I'll just keep the 6 outside. So that's 10 over W. And then it's over here 4 to, so that's 20 over W. So now I have C is equal to 20W squared plus, I distribute in the 6, I'll get 60 plus 120, so 180 over W. Okay, and then this is an optimization question, so now we have to find the derivative of C. So we'll get 40W minus 180 over W squared. That's our derivative. And we have to set this equal to 0. Get our critical point. So if we rearrange this, we'll get 40W equals 180 W squared, or 40W cubed equals 180. And then W is equal to, if you solve this out, it's equal to like cube root of 4.5. And then you're going to just plug in this W value back in for your cost. And you'll get your final cost as being 163.54. So does that problem make sense? Okay. So that's optimization. And then that's done. And then I'll go over, so I'm not sure, you guys have to let me know, but I don't know how much, what about integrals you need to know exactly. I went over the graded homework for it and I saw like, I know some examples to go over, but if there's anything further that you guys went over, let me know. So this is just one example. So if they're going to give you the derivative of something. And then they'll give you a condition saying f of 1 equal to -1. And then you have to find what f of x is equal to. So you guys should be able to know the formula is basically, if I want to take the integral of x to the n, it's going to be x to the n plus 1 divided by n plus 1. That's your formula. So I apply that to this. So 16x to the 4th divided by 4. 6x squared divided by 2. 7, and then x to the power of 1 divided by 1, basically. And then you have to include plus c always when you integrate. Okay, because c is a constant when you took the derivative. If you think about it, when I took the derivative of this, the c got lost at 0. Okay, so now you have to find what c is. I'm just going to simplify f of x. So that's 4x to the 4th, 3x squared, 7x, c. No, f of 1 is -1, so we know -1 is equal to 4 times 4. And solve for c, so -5, -8, -15. So c is basically, if you move everything over, you'll get c as -15. Then you have to rewrite your entire f of x equation. 4x to the 4th plus 3x squared 7x minus 15. Okay, so that makes sense, right? And if there's a if there's a question on anything I went over, you guys can let me know. I think one of you had a question about error, right? Oh, -1 is from the initial condition. So it said right here, this was just part of the question. F of 1 is equal to -1. Okay, so I'll go over that error question real quick again. Oh, do you guys need to know antiderivative trig? I didn't see that in the graded homework. Anything about it? Okay. If you don't, then I don't need to go over it. Oh, you... Okay, well, I'll go over it just in case it does pop up on your exam. But first, I'm going to go over to help on that error question. So this was the error question. And it asked you find the max error in the calculated area of the disk. So the first thing we did is we made an equation for area. Okay, so first for this one, we made an equation for area for the disk, and it's basically just a circle. So we know that area is equal to pi r squared. Then it wants the max error in the area. So we took the derivative on both sides. So we got dA over dr is equal to 2 pi r. And then with differentials, you're basically going to take this dr and move it to the opposite side so that you're just left with dA. Or dy, whatever it wants, whatever variable it's asking for. So we have dA is equal to 2 pi r times dr. We know what r is because it's given in the equation. It's 24 centimeters. So 2 pi, 24. We know the max error is 0.2. Max error gives you is equal to dr, dx, whatever, dt. That's what it gives you when it gives you the max error. So we plugged in 0.2. You plug in everything, and you get 50.15 centimeters squared, and that's your max error. So does that part make sense? Max error versus relative error. So max error is just what I just did. You're solving for dy or dA, whatever like your y variable is in that case. And relative error is dy over y, yeah. So it's what I just found divided by what y should actually be if there was no error. So if you look at what I did for relative error, I basically said, like if you plug in 9.6 pi in your calculator, you should get 50.15. I just wrote that for some reasons. Wait, 30.15, hold on. Let me go back to that question. I think I may have wrote the wrong number. Oh yeah, so this was not supposed to be 50, this is supposed to be 30.15. So yeah, if you plug in 9.6 pi, you get that same value. So basically the relationship for relative error is dA over A, dy over y, or whatever variable you're using, but it's comparing that error that you got with the area to the like what the area would ideally be. Yes, I found the relationship derived and then calculated dA. And yeah, I derived it with respect to R because that's whatever variable is giving you has an error, that's what you're going to take it with respect to. I didn't go over curve sketching for the sake of time, but I went over concavity, increasing, decreasing, max, min. After you find all of that with your equation, you can basically sketch the curve. I don't know how much of that will be on your exam, but if you have the intervals for everything that is increasing, the max, min, and the inflection point, then it should be relatively simple to find which curve is the right curve at that point. Yeah, symmetry is only if you have like a periodic function, like sine, cosine. MVT gives you global max, min, and first derivative and second derivative test give you local max, min. Yes, yes, they both give you. Oh, MVT gives you just it just tells you that the secant line and the tangent line will be the same at one point. So basically, I can show you for an example, like with Rolle's theorem. If I had a graph, and it was something like, well, basically it's like something like this, for example. Let's just call this C. It's saying f prime of C would equal 0 somewhere as long as these 2 points are equal to each other. So we'll call this f of A and f of B. Y-axis symmetry is even. Origin symmetry is odd. Yeah. Y-axis symmetry is even. Origin symmetry is odd. That's correct. Linearization question. Oh yeah, sorry about that. Yeah, it was over here. Okay. So did you have a question on it, or did you just want to see it? I will after he takes a look at the linearization one, and if he has any questions on it, I'll address that before I go back to the related rates one. Yeah, you don't plug in anything until you take the derivative for the related rates thing. Question. Optimization all in terms of one variable. I think you said you're getting 1.15 and 2.15. I'm not sure what method you're using. I would just do it this way because this method is pretty simple as long as you follow this equation. So as long as you first know what function you're working with, take the derivative of that function, and then find your A and f of A. And then you have everything you need to solve the question. You got 1 point less than you should have. So again, it's hard to tell exactly what method you're using just because there's no way for me to see how you did it. But if you were only getting one number or one value less than what you should have, it could have just been an algebraic error. But this is the only way I would recommend solving this type of problem. Yeah, I mean, I'm distributing if, like, the 1/4 is getting distributed at this point right here. It's going to be 1/4 times 0.6, basically. Okay. All right, sounds good. Good luck on your exam, everybody. Stay safe, and if you need any more additional practice material, you can always just look up optimization related rates problems. They're all online, and they have some pretty good practice. So good luck.